Hello everyone. Now I'm going to present our paper ezDPS, an efficient and zero-knowledge machine learning inference pipeline. I'm Haodi Wang. This is a joint work with Professor Wang at Virginia Tech. So I'm going to present the background introduction. Suppose we have a user who wants to perform some machine learning or deep learning tasks on a specific dataset. However, the user has very limited computation resources and thus cannot perform the computation by herself. Alternatively, the client could upload the data to a remote server and let the server do the computation. The server then returns the results. This procedure is known as machine learning as a service. Despite the effectiveness, the client cannot be sure whether the machine learning results are correctly computed or not. A malicious server might return a random result on purpose. To solve this issue, a straightforward way is to let the server release its model parameters. However, the training procedure is resource-consuming and contains expert knowledge. Thus, the parameters can be viewed as the intellectual properties of the server. Giving out the parameters will harm the server's interests. Fortunately, zero-knowledge proof as a powerful cryptographic primitive can help to solve this issue. There are two parties involved in the zero-knowledge proof scheme, a prover and a verifier. The goal is to prove the correctness of an NP relation with input X and the prover's witness W. The verifier wants to know if the relation is correct, while the prover wants to protect its witness W. To do so, the verifier firstly sends X to the prover, who will generate a proof pi. Then the proof returns back the proof pi to the verifier, who can verify the proof. If it passes, then the verifier accepts the statement. Zero-knowledge proof has the following properties. Completeness, which means the correct results could definitely pass the verification. Soundness, which means an incorrect result cannot pass the verification except for a negligible probability. Zero-knowledge, which means the verifier gets nothing about the witness information during the whole procedure. Based on the general zero-knowledge proofs, there is a commit and proof paradigm, which means the prover can prove upon the committed witnesses. In our machine learning as a service scenario, the client is the verifier and the server is the prover. X is the client's data and the witness W is the server's model parameters. To guarantee that the server will use an effective model to deal with the input, the server needs to firstly commit to the model parameters before the proving procedure. Thus, we're going to adopt the commit and proof scheme. The client then uploads the data and lets the server perform the machine learning task. The server returns the results, the integrity proof, and the commitment to the client, who can verify the correctness via the proof. There are a few works proposed in the literature about zero-knowledge machine learning or deep learning. However, they focus solely on single-stage or simple models such as the work for decision tree and CNNs. In fact, in real-world application, the machine learning tasks usually require multiple stages, which is called as machine learning pipeline. In this work, we focus on the machine learning inference pipelines with classical machine learning algorithms, because compared to the deep neural networks, classical machine learning contains more interesting operations for zero-knowledge proofs, and they are more appropriate for small and middle-sized tasks. Here is a typical machine learning pipeline, which contains 3 stages: preprocessing, feature extraction, and classification. In our paper, we aim to design an efficient zero-knowledge scheme for this typical structure. Our ezDPS realizes the following contributions. We present new gadgets for concrete machine learning operations, which are necessary building blocks in proving multiple machine learning algorithms, even deep learning methods. We also propose a new zero-knowledge machine learning inference pipeline scheme. We instantiate the machine learning inference pipeline with 3 concrete algorithms: DWT-based preprocessing, PCA-based feature extraction, and SVM-based classification. Our scheme is designed for a general zero-knowledge proof scheme, thus it is compatible with any zero-knowledge proof backend. The reason we choose this algorithm is that they are proven to be effective in multiple regions, such as signal processing, classification, and regression. Now we first present several gadgets as fundamental tools in constructing the arithmetic circuit. The exponent gadgets proves that b equals to a to the power of x. Here, the exponent x is the secret to be protected. The key idea is to pre-compute a multiplication tree and represent x in binarization. The greater than gadget proves that scalar a is greater than scalar b. The key idea is to observe the most significant bit of the difference between a and b plus a prime number p. Similarly, the absolute gadget proves that scalar b is the absolute value of scalar a. The difference between these two gadgets is that we deal with the most significant bit differently. And the maximum gadget first switches the first value and the maximum value, then proves the new vector is a permutation of the original vector and compares the first element with each element in the new vector. These are 4 examples of our gadgets. For more building blocks, please refer to our paper. Now having the basic gadgets, let's see how to prove the computation for each machine learning stage. Firstly, the discrete wavelet transformation-based pre-processing. To better illustrate our method, we use a small example where the input had 6 dimensions and the filters have 4 dimensions. Firstly, low-pass and high-pass filters are used to decompose the input data and obtain the low-pass part and the high-pass part. The high-pass part usually contains noise, thus need to be denoised and get Z4 prime to Z6 prime, which is the second step thresholding. The output of the thresholding and the inverse low and high filters are used to reconstruct the data, which is the output of DWT. The thresholding incurs a comparison with a parameter eta, which can be proved via the greater than gadget. The decomposition and reconstruction are convolution-like operation. Directly proving them requires linear time complexity. We use a split technique to reduce the complexity. More concretely, the computation of the decomposition obtains Z1, Z2, and Z3. The computation requires 12 multiplications. If we look at these equations more carefully and add the different powers of a random scalar alpha, we can adopt the random linear combination and have this. In this equation, d is the term that have to be subtracted from the left side. There are 16 multiplications in d, which is more than the original equations in DWT. That's because the step of the sliding window between 2 rungs is 2 instead of 1. To address this issue, our insight is to first split the input and the filter into 2 parts, the odd part and the even part. So alternatively, we split the input and the filters and compute each part respectively. We can apply the random linear combination separately to 2 parts and add them together afterwards. The complexity is reduced to 4 multiplications in total, thus reduce the number of constraints when proving. This is a simple example of the split technique. For more information, please refer to our paper. The second stage is PCA-based feature extraction. The computation of PCA can be simplified as a matrix multiplication between an input vector and a matrix of eigenvectors. Instead of computing this directly, we adopt the random linear combination with different powers of a random scalar and add them together to reduce the computation complexity. Therefore, the complexity is reduced from OMK to OK. Finally, for SVM-based classification, we use the radial basis functions at the SVM kernel, which can be proved by the exponent gadget. The SVM algorithm selects the class with the highest decision function value, which can be proved by the maximum gadget. We used the one versus rest strategy to deal with the multi-class classification. And to project the decision function to the class label, we use the value index pairs and adopt the permutation gadget to prove it. Our proposed gadgets and methods have more functionalities and can be adapted to other regions, such as the KPUA, proving other SVM kernels, deep learning methods, and zero-knowledge CNN schemes. Please refer to our paper for more details. Here are our experimental configurations. All the experiments were run without thread-level parallelization. We evaluate our scheme on 3 public datasets. We use Spartan as the ZKP backend and Herax as the polynomial commitment scheme. The machine learning parts are implemented in Scalar library. Here are the overall performance of our method. ezDPS is 1 to 3 orders of magnitude more efficient than the generic arithmetic circuits under the same ZKP backend. The verification and bandwidth in ezDPS are highly efficient. Here are the detailed performance of our method. The cost of DWT is stable and contributes a considerable portion to the overall performance. The cost of PCA processing is also stable and it contributes the least portion to the overall performance. SVM computation is the most dominant factor, especially on large datasets. There are some potential issues of our method that can be further discussed. The proving time for ezDPS is still high, and the size of the arithmetic circuit can be further reduced. Moreover, ezDPS incurs a certain accuracy loss due to the conversion between the floating point representations to the fixed point arithmetics. Finally, ezDPS cannot protect the privacy of the client's data, which is an open research question in the literature. In conclusion, we present several new gadgets for multiple machine learning and deep learning operations. We propose an efficient and zero-knowledge machine learning inference pipeline with optimizations to accelerate the proving and verification procedure. We fully implemented our scheme and provide the open source codes. This is the end of my presentation. Thank you for your attention. I would be happy to answer any questions.